Hello, everyone. Welcome to our lecture on Network and Media Lab. Before we start, I hope you and your families are doing well and staying healthy and staying safe. I do realize that this might be an overwhelming time for everyone. So if anyone would like to discuss anything or chat about anything, please shoot me a message on Facebook Messenger and I would be happy to talk. Last time we met, we discussed virtual LANs. Today is going to be our last lecture on the data link layer. We're going to discuss the spanning tree protocol, and the spanning tree protocol is actually a very important component, or very important part of the data link layer. Okay, so before we start discussing the details of the Stp protocol, let's first discuss its motivation. So in most networks, if not all networks, you do have redundancy at layers 1 and 2. Consider, for example, the figure that you see in this slide. You see here that you have 3 switches, S1, S2, and S3, and they are connected in a triangular graph shape. That means that there is more than one path from any switch to any other switch. This is quite often done intentionally, so that you have options to travel from one device to the other, so that if one link fails, for example, you can actually activate another link. However, having this redundancy in the physical topology of the network can create actually several problems. And I will start by illustrating some of these problems. Consider that you have these 3 switches. This is S1, this here is S2, and this here is S3, okay? And they are connected to each other in this triangular fashion. Obviously, there will be devices also connected to these switches, but let's just focus on the switches right now. Now, let's assume that switch S2, let's say, for example, it's connected to this device, and it receives a broadcast packet. So what does the switch do with a broadcast packet? It sends it on all outgoing links, okay? These 2 broadcast packets now arrive at switches S1 and S3. What does S1 do? It puts it on all outgoing links. So it puts it here. Switch S3 also puts it on this outgoing link. And so the broadcast packet will now arrive again at S1 and S3. What will they do? They actually will also send them on all outgoing links. You have to note that in layer 2, there is no time to live. We have the time to live field at the IP layer, at the network layer, which is basically a counter that prevents a packet from looping around the network indefinitely. There is no such mechanism in the data link layer. And so technically, there is nothing that would prevent the packet from looping around the network forever and ever. And this obviously becomes a big problem. This is actually something that is called a broadcast store. Because broadcast packets are so common in networks and they happen all the time, you might end up actually with a very high volume of traffic in the network just because of this structure, because you have a loop in the network that keeps actually sending packets in the network over and over and over again. This is the first problem. Second problem, let's say we have now the same topology. So we have S1, S2, and S3. Now let's say S2 receives a unicast packet. However, let's assume that the switches have just been booted, and so their MAC tables are empty. So if a switch receives a packet and it doesn't know its destination, what does it do? Obviously, it learns the MAC address of the sender. So it now knows that device A is reachable via this port, but it also puts the packet on all outgoing ports, uses the flooding mechanism. And so again, this packet will reach S1 and S3. Because they also don't know how to forward the packet, they will do the same. So this packet will now be forwarded by S1 to S3 and by S3 to S1. However, before forwarding, S1 will also learn the MAC address of the sender A. S3 will also learn the MAC address of A. However, S1 the first time it receives the packet will think that A is reachable via this port. While when it receives the packet a second time from S3, it will now think that A is reachable via this port. And so now it has to update its MAC table to verify or to indicate that A is now reachable via this port. This will keep happening because there is a loop. This will keep happening over and over again, and it will result in what is called the MAC table instability. The MAC table keeps changing. The switches will keep thinking that the devices are reachable via different ports and will keep changing its MAC table. This can actually lead to some devices becoming unreachable in certain periods of time if the MAC table indicates a wrong path. Okay? This is the second problem that we have. So now we have broadcast storms and we have MAC table instability. Let's see the third and final problem, or the final motivation behind the STP. We have the same topology. Now let's say that device A here wishes to send a packet to device C that is connected to this switch. So it's a unicast packet, sends it to S2. Let's say the MAC table is empty at S2. So it sends the packet on all outgoing links. S1 will receive it and will forward it to C. C is happy, it has received a packet that is intended to it. Now the packet reaches S3, and because it also doesn't know the destination, it sends it to S1. S1 receives the packet again. It has no mechanism to detect that it's a duplicate, so it sends it again to C, and now C receives the same packet twice, and so it receives a duplicate packet, and there may or may not be a mechanism to recover from that. So we can now see the three problems that arise because of this, the presence of this loop in the network. The first one is the MAC table instability. The addresses basically keep changing in the table, and there is no time to live field in the packet, so it might actually lead to some hosts becoming unreachable. We have also broadcast storms, and we have also duplicate unicast frames. By the way, broadcast storms can lead to denial of service if there is too much traffic, and it can actually build up quite quickly. It might actually lead to switches becoming congested and not being able to forward packets in this case. Okay, so if this is the situation, what does STP actually do about it? STP basically aims to establish what is called a tree structure in the network. And a tree, by definition, is a structure that has a single path from any node to any other node and has no loops. So basically, every node is reachable. Every node has a path to every other node, but there are no loops in the network. And so if you see the figure on the right, the one on the top, you have the three switches S1, S2, and S3, and they are connected in this structure. Obviously, there is a loop between them. The goal of the STP protocol would be to block one of the ports. In the figure that you see here, port F02 on switch 2 becomes blocked. If this port becomes blocked, now there becomes only one path from any switch to any other switch. Let's say, for example, PC1 wants to reach PC4. The only path will be PC1, then switch 2, then switch 1, then PC4. If PC4 wants to reach PC3, it has to use switch 1 and then switch 2. There is no option to go through switch 3 because the port between switch 3 and switch 2, which is F02, is blocked. Now note here that the link between S3 and S2 has actually two ports. There is port F02 on S3 and there is port F02 on S2. The STP protocol only blocks one of these two ports. So only port F02 on S2 would be blocked in this case. The other one may actually be forwarding packets to switch 2, as we will see in a little bit, but switch 2 will ignore these packets because the port is actually blocked. Okay, we will see the mechanism of how STP does that in a little bit. Basically, how do the switches actually exchange information so that they can establish this loop-free structure in the network? Through packets that are called Bridge Protocol Data Units, or BPDUs. These are control packets that are exchanged between the switches. Only the switches understand them, and they are part of the STP protocol, and they contain the information necessary for the switches to understand if there is a loop or not, as we will see also in a little bit. Okay, so in order to understand how STP works, before I actually show you the overview of the STP protocol, we have to dig a little bit deeper into the operation of the switch and understand how ports in the switch work. Basically, we want to understand what are the states of the port. Each port in the switch can actually be in one of 5 states: blocking, listening, learning, forwarding, and disabled. Disabled is the easiest one. If a port is in a disabled mode, that means it doesn't do anything. It doesn't send and receive BPDUs, so the STP protocol is not working. It cannot learn MAC addresses. It cannot forward frames. It is actually as if the port does not have electricity passing through it. The port is disabled completely. Now, if a port is in the blocking state, which is what we do here in this figure, we set port F02 in the blocking state. It means that it can only receive and process BPDUs. So the STP protocol is still working. If a port is in the blocking state, it can still understand messages related to the STP protocol, but it cannot do anything else. It cannot forward packets, cannot learn MAC addresses, cannot broadcast frames, cannot do anything. Now, why do we have this state? Why don't we just disable the port completely? Basically, we still want to have the redundancy feature that I discussed a while ago. We implement networks in the structure that you see here because you want the network to have redundancy. You want to have an option in case a link fails. And so the figure that you have here on the right, the one on the top, let's say we blocked the port F02 on switch 2. Now, let's say later the link between S2 and S1 fails, this trunk 1. The link between S2 and S1 fails. Now, the path that you were using to send packets from any device to any other device suddenly becomes unavailable. So what you want to do is that you would want to now activate port F02 on switch 2 and activate the link between S2 and S3. So now you would want the port not to be in the blocking state. However, how would you detect this in an automated way? Obviously, if you would do it manually, then you can just log into the switch and you just change the status of the port from disabled to whatever you want. However, we want the process to be able to recover manually because this is actually how networks would work and it is the right way to do things. How would the port detect that it has to switch from the blocking state to the forwarding state? Well, basically, it would have to understand BPDUs. And this is exactly what the blocking state does. It allows the switch to keep processing BPDUs, to keep understanding STP, so that if there is a failure in the network, it can actually recover and switch to another state. Okay, now, we want eventually that if there is a failure in the network, the port that was in the blocking state becomes in the forwarding state. And in the forwarding state, the port can do everything. It can understand BPDU, so it can still actually understand the STP protocol, but it can also send and receive frames. It can learn MAC addresses. It can send broadcast frames. It can do everything. However, between the blocking and the forwarding state, the transition is not direct. You can actually transition from forwarding to blocking right away without actually any delay. But you cannot transition from blocking to forwarding directly. First, you have to transition from blocking to something called the listening state. And in the listening state, the port is also only understanding STP. It cannot learn MAC addresses. It cannot send and receive frames. The difference is that the listening state is only a transitional state. The port will remain in this state for a limited period of time. Typically, it is 15 seconds. It will only remain in this state for a limited period of time, just so that if there are loops in the network, it can be figured out. So the switch remains in the listening state for a period of time, and it receives BPDUs to try to figure out if there are loops in the network. After that, it can transition then to the learning state. In the learning state, it can still receive and process BPDUs, but it starts also to learn MAC addresses. It is still not capable of forwarding frames and cannot actually process frames in this case, but it can start learning MAC addresses, meaning that if it receives a packet, it will save in its MAC address table the port from which the packet came, the MAC address from on the port from which the packet came. The learning state is also a transitional state, meaning that the port can only remain in this state for a limited period of time. Typically, it is also 15 seconds. And then it can transition to the forwarding state where it can do everything. So if a port is in the blocking state, it has to first transition to listening, then learning, and then forwarding state before it can actually send and receive packets. And if you want to do the opposite, if you have a port that is in the forwarding state and you want to put it in the blocking state, you can actually do it directly without having to go over any other states or phases. Okay. Now, what does this have to do with the STP protocol? Let's see our network that we want to fix. So we have S2 and S3 and S1, and they are connected in this structure. Now, our objective is to put one of the ports in the blocking state. Now, this is done by forming, as we said, a tree structure in the network. This is what the spanning tree protocol does. So just as an overview, the way the spanning tree protocol works is that first of all, you have to elect something called the root bridge. The root bridge is basically a switch in the network where that is going to be the root of the tree. Now, one of these three switches will become the root bridge. I will show you in a little bit the election process, but for now, let us actually assume that S1 has been elected as the root bridge. And by the way, this election process happens automatically. We will see it in a little bit. Now, if S1 becomes the root bridge, all the ports on S1 are directly put in the forwarding state. Okay, so now all the ports on S1 can send and receive packets. If the ports on S1 have been before in the blocking state, they have to transition to the forwarding state. But basically, all the ports on S1 are now in the forwarding state. Now, S2 and S3 now have to figure out which port becomes what is called the root port and which port becomes the designated port and which port becomes blocked. So each switch has to decide, first of all, which port is the root port. The root port is basically the port that has the lowest cost to reach S1. Okay, since S1 is the root bridge, S2 and S3 will know also that S1 is the root bridge. This is actually the result of the election process. So the result of this process is that S2 and S3 will now want to determine which port has the lowest cost to reach the root bridge. Now let's assume that S2 determined that this port is actually the root port. S3 has also determined that this port is the root port, meaning that they have determined that these two ports are the ones that have the minimum cost to reach S1. Note here that S2 has two paths to S1, one that is directly between S2 and S1, and one that is through S3. Now, one of these two will have a lower cost than the other. It might not be just for the number of hops. It might also depend on the speed of the links, as we will see in a little bit. But for now, let's just assume that S2 and S3 chose the root ports that I am showing you in this figure. Now, for these remaining two ports between S2 and S3, one of them becomes in the blocking state and one of them becomes in what is called a designated port. Designated port. Okay. Let's assume that this port right here becomes in the blocking state and the other one will become the designated port. Okay. I will show you how switches S2 and S3 will actually determine which port becomes the designated port and which one becomes the blocked port. Now, if we chose the port in S3 to become blocked, then S3 will have to put this port in the blocking state, meaning that it will continue to receive BPDUs, and but it cannot actually send and receive frames, and it cannot learn MAC addresses. This is the rough overview of how the STP protocol works. Now let's actually look at the details. These, first of all, are the port roles. So the port roles, we have one switch that is elected as a root bridge, as we discussed. Here in this figure, we have S1 elected as the root bridge. And if it is the root bridge, then all the ports are put in the forwarding state. For all the other switches, they have to elect one port as the root port, which has the lowest cost to reach the root bridge. And then you have the designated port. The designated port is basically selected on every link, which is basically the second best port to reach the root bridge. Okay. In newer versions of the STP protocol, particularly the rapid STP protocol, which we'll discuss in a little bit, there are two additional port roles. There is the alternate port, which is a backup port for the designated port. And there is something called the backup port, which is the backup port for the root port. So you have two backup ports, one for the designated port and one for the root port, and we will discuss it later in this lecture. Okay, so first of all, which switch in the network becomes the root bridge. Okay, this is done based on a number that is called the bridge ID or BID. The BID consists basically of three fields that we see them on the figure on the right. The three fields are the MAC address of the switch, the extended system ID, which is basically the VLAN ID, the ID of the VLAN to which the port belongs, and also something called the bridge priority. Okay. Collectively, these three fields make up what is called the bridge ID. And basically, the switch that has the lowest bridge ID becomes the root bridge. Okay, so again, collectively, these three fields, the bridge priority, extended system ID, and the MAC address, collectively make something called a bridge ID number. And the switch that has the lowest bridge ID becomes the root bridge. If you see the figure on the bottom, you have the three switches. Switch 3 and switch 2 have a priority 32769. So the bridge priority is set to 32769. And we see the MAC addresses here. Switch S1 has priority 24577. Now, if you put the bridge priority 24577 next to the MAC address which is 000, A00, 333, and all those three, this here is actually the collective bridge ID. And so if you compare that to the bridge ID of switch 2, which is 32769, and then 000A00111111, you will notice that the bridge ID of S1 is lower than the bridge ID of S2, and so S1 becomes the root bridge. Same comparison can be done with S3. Now, by default, the bridge priority is set to 32768. If you add to it the VLAN, by default, all the ports are in VLAN 1. So 32768 plus 1, that means that the priority in total is 32769, which is the figure that you see in the number that you see in the figure on the bottom. You can actually change the priority field. So for example, here, switch S1, the priority is set to 24577. That means someone has actually logged in the switch and changed the bridge priority. You do that if you want to force a certain switch to become the root bridge. Quite often, network administrators want to do that. For example, you have a switch that is more powerful, or you have a switch that is in a centralized position in the network. It is close topographically to all the other switches, or it has better access, or it has better security features, or whatever that you want. You can actually enforce a certain switch to become the root bridge by setting a lower priority. The lower the priority, the higher the chances of this switch becoming the root bridge. Now, you will see here that the bridge priority is the field that makes up the most significant numbers in the bridge ID. And so if you set it to a lower value, that means you are giving it a higher priority to become the root bridge. But as we said, by default, the bridge priority is set to 32768. Now, imagine you have a situation where the bridge priority is set to the default value. All the ports are members of VLAN 1, and basically all the switches have the same numbers. What would actually make the switches elect the root bridge? The only field that would make this decision is the MAC address. So if the bridge priority is not changed, and if there is only one VLAN, then the switch that has the lowest MAC address will become the root bridge. Okay. Okay. The first version of the Stp protocol, which is called 822.1d, didn't consider VLANs. So there was only one VLAN for all the devices, as we'll see in a little bit. So basically here in this case, the extended system ID would not have played a role in this case. Okay. The second thing that we will discuss is the cost of each path. Okay. In the IEEE specifications and the Ethernet specifications, each port is given a certain cost depending on its speed. So if you have a port that is a gigabit port or a 10 gigabits per second port, as we see in the table here, its cost will be 2. That means the cost of sending over this link will be 2. If you have a port that is 1 gigabits per second or a link that is 1 gigabits per second, this cost is 4. And if it's 100 megabits per second, the cost is 19. And if it is 10 megabits per second, the cost is 20. Okay? So if you see the figure on the left, Let's try and find the cost of path 1, which is basically the path from S2 to S1. If this is a link that has 100 megabits per second, the cost of sending over this link will be 19, according to the table. Okay. Um, uh, on the other hand, if you have path 2 actually has two links from S2 to S3 and then from S3 and to S1. If both links are also 100 megabits per second, then the cost is 19 plus 19, or 19 times 2, which is 38. So this means that from the point of view of S2, path 1 has a lower cost, and so it will elect this port to be the root port. Okay, this is how this is how the switches determine which is the root port and which is the designated port. Now, just as you can change the priority field in the bridge ID, you can also change the spanning tree cost. So you can define for every interface what would be the cost. This would be, for example, if you don't want a certain link between switches to be used. You want to, for example, reserve it for something else. You don't want it to be used by the spanning tree protocol, or you want to give it a lower priority. You can actually set the spanning tree cost as you see in the instructions on the right. Okay. By the way, the figure on the bottom right corner, which says the command says show spanning tree, that actually tells you the spanning tree from the point of view of the switch. In this case, it is switch 2. So here, if you look at the fields, show spanning tree, first of all, tells you what is the root bridge. This is actually the root bridge from the point of view of S2. And if you look at this information, you will find that the root bridge is actually S1. And then after that, you have the bridge ID. This is actually the bridge ID of S2 itself. You have a bunch of parameters and timers, hello time and max age. I'll discuss them in a little bit. And then at the bottom, you have the states of the ports in S2. You have F01. It is actually the root port, and it is set in the forwarding state. And then you have F02. It is the designated port, and it is also set in the forwarding state. You have to remember that if you have the link, as you see in the figure on the left, you have the link between S2 and S3. One of them will have the designated port and the other one will have a blocked port. So in this figure, S2 actually has the designated port as indicated by show spanning tree, and the designated port is set to the forwarding state because the designated port will actually forward packets, but the blocked port on S3, as you see in the figure, will not process these packets. The blocked port will actually drop these packets. Okay. Okay. So given all of that, you can actually determine everything in the network. You can determine the port roles. So we know how the root bridge is elected. Everyone knows their bridge ID. You can set priorities. So for example, in this figure here, S1 has the lowest bridge ID, and so S1 becomes the root bridge. And based on that, you can determine using the cost of each link, you can determine what is the root port. And so F01 on switches S2 and S3 become the root port. And after that, you can determine what is the designated port and what is the block port. Now, between S2 and S3, you will see actually that F02 on S2 and S3 have an equal cost to S1. And so none of them would actually have a preference to become the designated port while blocking the other one. If there is a tie in the path cost between two switches, they use the same process to actually determine which one becomes the designated port. So first they look at the priority field. If it matches, they look at the MAC address. If it matches as well, then the MAC address obviously will not match. Then the one that has the lower MAC address will be the one that is elected as a designated port, and the other one will be in the blocked state. So you can see here that in S2, the bridge ID is 32769, and the MAC address is 000A00 and then all ones, while in S3, the bridge ID is 32769, so it has the same priority, and the MAC address ends in all twos. So switch 2 is the one that has the lower bridge ID. Obviously, it's not the root bridge, but this is why F02 on S2 is the one that becomes the designated port, while F02 on S3 becomes in the blocked state. Okay. Okay, we have discussed that. How do actually switches communicate with each other to achieve all of that through a packet that is called the BPDU, the Bridge Protocol Data Unit. These are the packets that the switches exchange with each other so that they can enforce the rules of the spanning tree protocol. And the BPDU frame has a certain set of fields. The first four fields, as we see here, they are the protocol ID, set to 0 by default, the version, the message type, and the set of flags. The flags basically allow the switches to tell each other what has happened. For example, you can set a flag to tell the switch that there has been a change in the topology that has been detected, so that it can actually prep them to change a port from the blocked state to the listening listening state. Okay. By default, the protocol ID and the version field and the message type are all set to 0. This is in 822.1d. In later versions of the protocol, they are set to different values. Then you have fields 5 to 8. This is actually the root ID, the root path cost, the bridge ID, and the port ID. The root ID is basically the ID of the bridge. This is the bridge ID, the one that has the priority plus the MAC address. The root path cost is the cost from this switch, the one that is sending the BPDU, to the root bridge. And the bridge ID is the BID of the current switch. And then the port ID is the ID of the port that is sending the BPDU. So these four fields actually determine a lot of information about the STP protocol itself. Whenever a switch sends a BPDU, it will indicate in it what is the bridge ID of the root bridge. So it will indicate from its point of view which bridge it thinks is the leader of this process, which bridge is actually the root bridge. It will also indicate the cost from this switch to the root bridge. It will indicate its own ID, its own bridge ID, and it will indicate the port number from which the BPDU is being sent. And finally, you have the fields from 9 to 12. They actually contain a set of timers. You have hello time. Hello time is basically the time between root bridge messages. Basically, once the STP protocol establishes the loop-free structure, the root will keep sending hello messages to just tell the other switches that it is still there. Okay. Usually, the time between these root bridge messages is 2 seconds. Obviously, networks are not perfect, so sometimes there will be delays, sometimes this packet will be lost or not sent for any reasons. It could be that the link is actually failing. And so you have another timer, which is the message age. The message age is the time since the root bridge sent the last configuration message. And then you have max age. The max age is the maximum time before a switch would determine that something has gone wrong. It's actually the max time, so that if the switch has not received the hello message, it will determine that the link has failed. And then finally, you have the forwarding delay. This is actually the time the bridges should wait before transitioning to a new state. So from listening to learning, it waits for the forward delay. From learning to forwarding, it waits also for the forwarding delay. These are the delays and the IDs and the fields that you have in a BPDU frame. Okay, so now let's discuss the details of the STP protocol. Given all of that, how do the switches elect the leader? How do the switches elect the root bridge? Okay, if you elect the root bridge, then everything becomes easy after that. Once you elect the root bridge, the other switches can determine what is actually the best path to the root bridge based on the cost, and what is the designated port and what is the blocked port. Okay, so how do the switches elect the root bridge? Basically, when you plug in the switch and power it on, the switches are selfish. Each one of them will assume that it is the root bridge. So if you see the figure on the bottom, S2 has just been powered on, and so it assumes that it is the root bridge. And so it sends the BPDU that includes the root ID equal to the bridge ID. So it sends a BPDU where the root ID is equal to its own bridge ID. Therefore, it is telling everyone that it is assuming that it is the root bridge. And it sends this BPDU to S3. Okay, it will also send it to S1, but for now, let's say it is received by S3. Now, S3 also will do the same. It has received this BPDU from S2. S3 previously would assume that it is also the root bridge. Okay, Now, when S3 receives the BPDU from S2, it will compare the bridge ID with its own bridge ID. Now, the bridge ID of S2 is 32769, and then the MAC ends with ones. The bridge ID of S3 is also 32769, but the MAC address ends in twos. So the bridge ID of S2 is lower than the bridge ID of S3. And so S3 now confirms that S2 is the root bridge. So in the first BPDU sent by S2, S2 is assuming that it is the root bridge. Once this packet arrives at S3, it will confirm that S2 is the root bridge. And so it will send this packet to S1. Now, S1 receives a BPDU from S2 and will receive a BPDU from S3. S1 will do the same. S1 will compare the bridge ID with its own bridge ID. However, if you take a look at the bridge ID of S1, we'll see that its priority is 24577. And so its priority is lower than the priority of S2 and S3. And so it will have a better chance to become the root bridge. And so when S1 receives the BPDU from S2 and S3, it will ignore them both. It will not confirm that this is actually, that S2 is the root bridge. It will actually ignore them both. And then eventually what S1 will do is that S1 will also send a BPDU. Okay? When S1 sends the BPDU, it will include its own root ID equal to the bridge ID, telling S3 and S1 that it is the root bridge. And now S3 and S1 will receive this BPDU from S3 and S2 will receive this BPDU from S1 and will compare the bridge ID, their own bridge ID to the bridge ID of S1, and will determine that the bridge ID of S1 is lower, and so they will both confirm that S1 is the root bridge. And so the next time S2 and S3 will send the BPDU, these BPDUs will confirm that S1 is the root bridge. So if we repeat that, how did the process actually start? It started by S2 sending a BPDU, assuming that it is the root bridge. S3 receives this BPDU and S1 will also receive it. S3 has a higher bridge ID, and so it will confirm that S2 is actually the root bridge and will send a packet accordingly to S1. And so S1 will receive two BPDUs, one from S2 saying that S2 is the root bridge, and one from S3 saying that S2 is also the root bridge. S1 will compare its own bridge ID with the root ID that is sent, which is the bridge ID of S2, and it will determine that it has a lower bridge ID, and so it will determine that it is or it should be the root bridge. And once it sends the BPDU to S2 and S3, they will also confirm that. So this process ends with all the switches learning that S1 is the big boss, S1 is the root bridge. And now the remainder of this process, the other switches have to determine what is the root port and what is the designated port. Because they know what are the links that are connected to S1, for example, S2 knows that F01 is connected to S1. So it knows the cost of this path. So it can actually compare whether the path to S1 is shorter or the path to S1 through S3 is shorter. How does it do that? If it receives the BPDU directly from S1, then it knows that S1 is one hop away, and it knows that trunk 1, which is connected through F01, has the cost that is actually in the BPDU message itself. However, when the BPDU comes to S2 through S3, S3 will increment the cost. So S3 will increment that the cost to go to S2 through S1 is actually 38. It's 19 plus 19. And so S2 will know that the cost to S1 is longer through S3, and so it will elect F01 as the root port, and F02 will become the designated port. Now, S2 and S3 will also send BPDUs to each other, and so they will know what are their bridge IDs, and so they will know that S2 has the lower bridge ID, and so F02 on S2 will become the designated port, and now S3 will know that it should put F02 in the blocked state, and so it will do that. Okay. Before we proceed, let's take a look at an example on packet tracer. Now, once I load this example, I want you to take a look at the these orange dots on the switches. The orange dots means that the STP protocol has not yet finalized. And so if we just leave the network, not do anything, and just leave the network as it is, eventually you will see these orange dots turning to green. If they turn to green, it means that these ports have been switched to the forwarding state. Okay, so if we forward the time a little bit, you will see that some of the ports are now in the forwarding state and some of the ports are in the blocked state, meaning that the STP protocol has actually finished the exchange between the devices, and now it knows which ports are designated ports and which ports are blocked ports. Now, if we go to the simulation mode, okay, and now let's try to ping between PC1 and PC6, okay, you will see the packets here. Now, I want you to take a look at how the ARP packet travels from PC1. So first, PC1 sends it to A1, which sends it to D2. Now, take a look at D2. Take a look at what D2 will do, how it will send the packet. It sends the packet to the switch A2, the switch A3, and the switch C1. But it doesn't send the packet to the switch C2. Why? Because you will see the orange dot here at the switch D2. It means that this port is blocked. And so it doesn't forward the ARP packet over that port because the STP protocol has blocked this port. So they will forward the packets here. And then after that, okay, and then the packet makes its way, and then the ARP, you will see here the two devices, PC4 and PC5 received it, PC6 also received it, and it is actually the right one. So it will start forwarding the reply back. Now you can see how the reply will travel back to PC1. So you can see here, switch A6 has two ports. One of them has the green arrow on it, while the other one is blocked. And so you will see here the packet will travel over the port that is now labeled as the root port. Okay, will travel back to A1, and now the ping packet can travel over the same path. Now, what we will do is we will generate a new scenario, and let's try and okay. Okay, if we if you cut this link between A1 and D2, you will see that the ping packet no longer takes the same path. Okay. If you go here, sorry, if you go to this link here and delete this link, okay, and now let us actually try and do the ping process again to ping between PC1 and PC6. Okay, you will see here that the link between A1 and D2 is no longer available, and now the packet has to actually travel over a different path because the STP protocol will now actually detect that this has taken place. Sorry about that. So if we try now and do that, so in A1, now you see that the path between A1 and D1, now the port is no longer blocked. It has a green arrow. And so the packet goes from A1 and then it goes to C1. And so there is a different path now between PC1 and PC6, and STP protocol has recovered automatically from this problem. Okay. I will send you actually this experiment. What I want you to do is try to delete more of these links and see how STP will actually update the topology automatically as you delete links. Okay. Now let's go back to our presentation. Okay. So this process works fine. except for a certain issue that creates a lot of problems with the traditional version of the STP protocol, which is 822.1d. And the problem actually has to do with what is called the protocol convergence. So you would notice from the experiment that we just did that it takes a little bit of time for the STP protocol to put all the ports in the correct state after an error has happened, after you delete the link. It takes a little bit of time to do that. Now, how much time would it take? Basically, the root bridge will send a hello message every 2 seconds. These hello messages, normally, sometimes they are lost. And so if you lose one hello message, it's not an indication that there's something wrong with the link. In the old version of the STP protocol, you have to pass a time that is called the max age. The max age is actually set to 10 hello timers. That is 20 seconds, meaning that you have to wait 20 seconds before you determine that something has gone wrong with the link. Okay. Now, after you wait 20 seconds, what do? The blocking port now has to be switched back to the listening port. And sorry, the blocking state, the port in the blocking state has to be now put in the listening state. And it has to stay in the listening state for 15 seconds. And now it can transition to the learning state where it stays for another 15 seconds and then it goes to the forwarding state. And so if we illustrate the total delay there, let's say you have this topology. Let's say you have, this is the root bridge. These two ports are in the forwarding state. This is the root port. This is the root port. This is the designated port, and this is blocked. Okay. Now let's assume that this link has failed. How would switch S2 detect this failure? Basically, S1 will be sending hello messages every 2 seconds. And so S2 will have to wait for max age. It has to wait for 20 seconds until it determines that the link between S2 and S1 is no longer active. It has to wait for 10 hello messages not to arrive. Okay? After this happens, S2 will be sending BPDUs to S3. This is actually the importance of having the port in S3 in the blocking state, because it continues to receive BPDUs. And so now S3 will determine that it has to transition its blocked port to the forwarding state. And so it will put the port first in the listening state, where it just listens for BPDUs just to allow the STP protocol to converge, and it stays there for 15 seconds. And then it transitions to the learning state, where it stays there for an additional 15 seconds, and then it goes to the forwarding state. So you have a total 50 seconds to recover from an error. Now, it used to be okay. It used to be fine to wait 1 minute or close to 1 minute once an error occurs in the network. By modern standards, this is obviously no longer acceptable. So you need the protocol to converge much faster. Okay, and so there has been several modifications of the 822.1d standard to allow for faster convergence. The one that is also proposed by the IEEE is called the Rstp, or Rapid STP, which has the number 822.1w. There are also other versions that we'll discuss some of them, that allows an STP or a spanning tree to be established per VLAN. We'll discuss first the Rstp protocol. It still only maintains one STP in the network, but it has faster convergence. Basically, it has several features. First of all, it doesn't wait for 20 seconds to establish that a link has failed. It waits only for 3 missed BPDUs. So it has a shorter time to indicate that a message has failed. It also has 2 new protocol states, the alternate port and the backup port, that allows also the devices to recover from an error faster. Another important feature that it has is something called an edge port. Basically, where do switches need to make sure that there is no loop? Basically, whenever there is a link between 2 switches, but the link between the devices, the end devices, and the switch itself are relatively safer. So in Rstp, they define these links to, or define these ports to be edge ports. These are the ports that are actually connected to an end device. What happens is you set these ports in a state that is called port fast. And the port fast state disables STP. So all the STP processes are no longer exist. Obviously, this is dangerous because STP is there for a reason. So if you remove, for example, PC1 and connect a switch instead, the port here would have STP disabled. And so it would be dangerous because there might be loops in this case, and you have the same problems as if you don't have STP at all. And so our STP also has something called Bpdu Guard. Once you disable a port, once you put a port in the port fast state, Bpdu Guard just monitors the traffic on this port and makes sure that no BPDUs are actually received. If a BPDU is received on an edge port, then it is no longer put in the port fast state and it starts actually becoming just a regular port enabling STP again. Okay. The other modification on STP is called per VLAN STP. Okay. Now, per VLAN STP allows you to create a different spanning tree for each VLAN that you have in your network. Why would you want to do that? In the original 822.1d, the original STP protocol that we have been discussing, all the VLANs use the same STP structure. That means that there will be one link that is blocked for all VLANs, and all the other physical links will be used by all the VLANs. Obviously, there is no load sharing. That means you're actually turning off one of the physical links in your network, never to be used. However, this has a low CPU utilization because there's only one instance of STP. Now, the PVST protocol, the per VLAN STP, allows you to have a different STP, a different spanning tree for each VLAN. As you see in the figure on the right, you can choose this switch to be the root bridge for VLAN 10, where you have this switch is the root for VLAN 20. And so this port here will be forwarding for VLAN 20, but blocking for VLAN 10, meaning that this link here will be used in VLAN 20, but not used in VLAN 10. And the opposite is in the other link. You can have this link forwarding for VLAN 10, but blocking for VLAN 20. So at the end of the day, you're actually using all the links in your network, but you are still avoiding the issues of the broadcast storm and the MAC address instability, because when you have different VLANs, the broadcasts are actually restricted between them. One VLAN does not broadcast for another VLAN. And so it is actually safe to have different spanning trees for different VLANs in this case. And this is exactly what a PVST does. However, this actually puts a strain on the CPU because now it has to process different spanning trees. How do you actually indicate that a spanning tree is in one VLAN or the other? Using the field that is called the extended system ID. Basically, this is added to the VLAN priority to make up the total bridge, the bridge priority to make up the total bridge priority in this case. And so the PVST uses this value to learn the identity of the root bridge and the root port and the designated port and all of that per VLAN. Okay. There is also a version that has been produced by Cisco, which is called Rapid PVST. It is also per VLAN, so it has the same features as the per VLAN STP protocol. However, it also has the features of the Rapid STP, meaning that it allows for faster conversions, meaning that it detects failed links quickly. It has the two new types of ports, and it has the port fast feature and the Bpdu Guard and all of those nice features that Rapid STP has. Okay. I will show you just some configuration messages that would help you when doing the experiment because we're almost out of time. These are basically the default values that are enabled on a switch. So the spanning tree costs are by default 4, 19, and 100 for 1 gigabits per second, 100 megabits per second, and 10. You have the switch priority 32768 by default. The spanning tree VLAN priority is 128 by default, and the timers, you will see them here. These are actually the default timers, the low timer, forward delay, and maximum age, and you can change any of that, as I said. Okay. There is also another version of the STP protocol that is called Mstp. Basically, if you have a very large number of VLANs in your network, let's say you have 100 VLANs, it becomes very difficult for the switches to actually maintain this large number of spanning trees. And so the MSTP, what it does is that it allows you to create a certain number of instances of the spanning tree. Let's say you create a total of 10 spanning trees. Now, what you do is, if you have 100 VLANs, what you do is you take each group of VLANs and you assign them to a spanning tree. So you say, for example, VLAN 1 to 10 are in spanning tree 1. VLANs 11 to 20 are in spanning tree 2. And you take your 10 spanning trees and you assign each one to a group of VLANs. They are easier to manage and they achieve load balancing, and it's the same thing without actually putting a large strain on the CPU of the switches. And this is in case you have a large number of VLANs. Okay, you can also set priorities for the route. So you can have a primary route and a secondary route. This helps with establishing the bridge election process. Okay, and you can have commands that basically enforce load balancing. You can say, for example, that this switch has priority for VLAN 20. So for example, here, switch S3 has priority 4096 for VLAN 20, and this switch has priority 4096 for VLAN 10. So you can set different priorities for different VLAN to enforce that different switches are elected as the root bridge for different VLANs in this case to achieve the load balancing feature. Okay. As we said, we talked about this before, the show spanning tree command allows you to actually see how the spanning tree is established in your network, so you can verify where is the root bridge and where is the designated, where is the root port, where is the designated port, and what is the status. Okay. And finally, you can actually verify the spanning tree mode. Some commands here, you can take a look at them and you will try them out in the lab experiment that you will do on the spanning tree protocol. Okay. That's it for this lecture. I hope you will stay safe. I hope that you will find the time that you are staying at home an opportunity to actually learn a little bit and enjoy the process. Thank you very much, and we'll see you next.